The last thing NASA's Opportunity rover ever sent back from Mars was a photograph of an empty sky. Half of it never arrived. It looks like a goodbye. It was not. On the 10th of June, 2018, with a planet-wide dust storm closing over it, the rover turned its camera directly at the sun and measured how much light was still getting through. Then the transmission stopped partway, and the rover never woke up again. That final image was not a farewell. It was data. And the storm it was measuring in those last minutes may be one of the mechanisms that stripped Mars of its water. Which means what Opportunity saw before it disappeared was not the end of its own mission. It may have been a record of the end of an ocean. So, let's go back. Opportunity landed on Mars in January 2004 alongside an identical twin named Spirit. Both were built and flown by NASA. The mission they were sent to perform was scheduled to last 90 Martian days, 90 sols, about 3 months. Both rovers are solar-powered, which sounds simple until you understand what that actually commits you to. Mars takes about 1.88 Earth years to go around the Sun, and like Earth, it sits on a tilted axis. So Mars has seasons, the same seasons we have, running at nearly double the length. Both rovers landed in the southern hemisphere, where the winter sun hangs low in the northern sky, which means that for months at a time, the only way to get useful power is to physically tilt the entire vehicle northward and hold it there. That is the job of the power team. And this is where a person enters the story. Jennifer Herman is the Power Subsystem Operations Team Lead for Opportunity at JPL. She did not start on the project at the beginning. She came on around Sol 300, roughly 10 months in, when the rovers had already outlived their design lifetime more than 3 times over. She has said that when she arrived, she was told not to get too settled in. The expectation on the team was that Spirit and Opportunity probably would not survive their first Martian winter. Think about what that means as a working condition. You are hired onto a project that everyone assumes is about to end. Every sol you get is borrowed, and then it does not end. It keeps not ending for 14 more years. And you are still there, still counting watt hours, still deciding how much science the rover is allowed to do tomorrow based on how much sunlight it can scrape off a dusty panel today. Herman does the same job for NASA's Curiosity rover, but Curiosity runs on a radioisotope thermoelectric generator, a nuclear power source. Curiosity does not care about the weather. As Herman has described it, relying on solar energy for Opportunity kept the team constantly aware of the season and the terrain in a way that Curiosity simply never demanded. The consequences of that difference are not theoretical. Spirit died in its 4th Martian winter, in 2009, not from a systems failure. It had lost the use of 2 wheels, long past their planned lifetime, and it became stuck in a sand trap. Once stuck, it could no longer maneuver itself into the favorable northward tilt. It could not point at the sun, so it could not maintain enough energy to survive the cold, and it stopped. Opportunity learned from that. By its final years, the team was driving it in a very specific way, planning routes so that every rest stop between drives was on a north-facing slope. They called those stops lily pads. The rover would hop from one lily pad to the next, like a frog, never committing to a route unless there was somewhere safe to land at the end of it. It worked. In the winter of 2011 and 2012, the rover was so short on options that it spent 19 weeks parked in one spot, because nothing else with a favorable tilt was within safe driving distance. It survived that. It survived 7 more. And on top of tilt and daylight, there is one more variable that decides everything: dust. Dust settles on the solar array constantly. Wind sometimes cleans it off. Wind also stirs up storms that block sunlight and then drop more dust onto the panels when they clear. Going into the autumn of 2017, Opportunity's array was dustier than in all but one previous autumn. The team was worried. Then, that winter, the rover got some unexpected cleaning events. Herman's assessment afterward was, on paper, optimistic. If the arrays kept getting cleaned the way they recently had been, the rover would be in a good position to survive a major dust storm. Then she added a caveat. It had been more than 10 Earth years since the last big one. They needed to be vigilant. That was December 2017. 6 months later, the sky went out. But we're getting ahead of it. Because to understand what the rover was doing on its last morning, you have to understand where it was standing. Opportunity arrived at the western rim of Endeavour Crater in August 2011 at a location called Cape York. Endeavour is a big feature about 22 kilometers across, or roughly 13.7 miles. For scale, that is a hole in the ground you could not walk across in a day. At Cape York, the rover found signs of past water and ancient clay minerals. Then, it kept going. Over the following years, it drove about 12 kilometers, more than 7 miles, climbing, driving, and sliding through the rim segments, until it reached a place called Cape Byron. And at Cape Byron, there is something that exists nowhere else on that crater rim. From orbit, the high-rise camera on NASA's Mars Reconnaissance Orbiter had photographed a notch cut into the crest of the rim. Below the notch, a system of shallow troughs runs downhill toward the crater floor, descending east at about 15 degrees, over a distance of roughly 200 meters, about the length of 2 football fields. And partway down, the troughs split. They branch apart and rejoin, weaving into each other in a pattern geologists call anastomosing. That is what a river system looks like. The mission's project scientist, Matt Golombek of JPL, put the reasoning very plainly. That, he said, is why they went there. The feature was named Perseverance Valley. The rover first reached its rim on the 20th of May, 2017, and drove over the edge and into it that July. It was the first time in history a robot had stood inside a feature like this and looked at it from ground level. The objective was simple to state. Work out the shape, work out the composition, work out how it formed, and if possible, roughly when. Now, that timing question matters more than it sounds. Mars has 3 broad chapters in its geologic history, defined by counting impact craters on its surface. The Noachian, from about 4.1 to 3.7 billion years ago, when the oldest surviving surfaces on Mars formed, when asteroids and comets were still hammering the planet regularly, and when liquid water carved river valley networks and filled lakes and possibly an ocean. Then the Hesperian, from about 3.7 to 3 billion years ago, vast lava plains, and catastrophic releases of water that gouged enormous outflow channels. And then the Amazonian, from about 3 billion years ago to right now, cold, hyper-arid, and essentially the Mars we see today. So, if Perseverance Valley was carved by water, it is a fossil, a trace of a version of Mars that has been gone for billions of years. The rover drove in expecting to confirm that. Here's what it found instead. The single most important thing Opportunity discovered in Perseverance Valley was not a rock, it was a direction. At a site called La Bajada, named after a stop on the old trade route between Mexico City and northern New Mexico, which is where the team drew all its names in the valley, from the rover came across 2 distinctly different rock outcrops separated by the path of the valley itself. Bright, flat rocks on one side, lumpy, darker rocks on the other. On one of them, the science team spotted erosion features called wind tails, streamlined tails of rock left behind when blowing sand carves away everything around them. Wind tails point. They record the direction the erosion came from. The rover was so interested that it backed uphill and popped 2 of its wheels off the ground to hunker down over the outcrop and look closely. And the direction those tails pointed was uphill. Sit with that for a second, because it undoes the whole premise. The rover had driven into a feature that looks from space like it was carved by water flowing downhill, and the clearest erosional signature on the ground says the flow went the other way, up and out of the crater. Wind on Mars blows radially up and over crater rims. Water does not do that anywhere. The mission's principal investigator, Steve Squires of Cornell University, summarized the problem with about as much precision as it can be summarized. Mars is a strange place, he said, but not so strange that water flows uphill. Now, at this point, most stories would pivot. Water theory dead, wind theory wins, roll credits. That is not what happened. And the reason it did not happen is the most interesting thing about how this mission was run. From the beginning, before the rover had even approached the valley, the team declared its approach: multiple working hypotheses, not a leading theory with alternatives listed politely underneath. Several theories, held simultaneously, all treated as live, none allowed to win early. This is not a modern idea. It comes from an American geologist named Thomas Crowder Chamberlain, who published a paper called The Method of Multiple Working Hypotheses in the journal Science in 1890. Chamberlain's argument was that when you approach a complex problem, carrying several hypotheses at once forces you to stay objective. He also argued something subtler, that many geological problems are best explained not by one process, but by several different processes acting at different times, or all at once, across history. Squires described the failure mode this approach is designed to prevent. The worst mistake a scientist can make, he said, is, "I wouldn't have seen it if I hadn't believed it." So the team started with 3 hypotheses for Perseverance Valley: a dry avalanche, a debris flow, or fluvial transport actual flowing water. Let's take them in order, because the order is instructive. The dry avalanche went first. Squires personally ruled it out, and the reasoning is refreshingly unglamorous. The slope is only about 15 degrees. That is too gentle. And the rover found no deposits of anything at the bottom that would indicate material had come crashing down the slope. No avalanche debris, no avalanche. Water and debris flow survived. Then 2 new hypotheses arrived that nobody had started with. The first came from Larry Crumpler of the New Mexico Museum of Natural History and Science, who had been mapping the structure of Endeavour's rim as the rover drove along it. He noticed the rim is not continuous. It is broken into segments, each a couple hundred meters long, offset from one another, oriented differently. And every time the rover crossed from one segment to the next, the underlying geology changed subtly, chemically, structurally. That is what a fault looks like from the surface. Inside the valley, Crumpler mapped a linear feature several centimeters wide, running downslope through impact breccia, characterized by a long zone of parallel red and gray material. It continued for 50 or 60 meters, parallel to the Labajada feature. When he mapped the fractures at Labajada, he found a fault bounding the margins of one of the troughs, which raises a genuinely uncomfortable possibility. Crumpler put it as a question: is Perseverance Valley just a graben? A graben is a block of ground that has dropped down between 2 faults, a rift, nothing to do with water at all. He thinks the real answer is more complicated than that, but his conclusion stands. There is evidence the valley's structure was controlled by a major fault, one that likely influenced how fluid moved through the crust. The second new hypothesis came from Rob Sullivan, also of Cornell, and it introduced a factor that quietly threatens every version of the water story. Sullivan studies wind erosion, aeolian abrasion. Wind-driven sand striking rock does not just polish it, it removes enormous amounts of material and leaves diagnostic textures on whatever remains. You can see it on Earth, in places like the Coachella Valley in California. His key point is about speed. On the plains Opportunity crossed on its way to Endeavour, ejector blocks thrown out by recent impacts have been visibly eroded on timescales of hundreds of thousands of years. Geologically, that is instant. So here is the problem. And it is a good one. If wind erosion on Mars is that fast, and this valley formed in the first half of Martian history, how did it survive for more than 2 billion years still looking like a river system? It should have been erased. But if the valley is young enough to have survived, then water flowed on Mars far more recently than anyone thinks, in exactly one location on one crater rim, and nowhere else. Where would that water have come from? Both branches lead somewhere uncomfortable. That is usually a sign you are looking at a real problem rather than a solvable one. And there is a detail buried in this that is worth holding on to. Every version of this story, water, ice, seepage, spillover, requires water on Mars and then requires it to be gone. The rover was standing in a channel that looked like a river, on a planet with no rivers. And nobody has ever fully explained where the water went. Keep that in your pocket. We will come back to it. Now, the anomalies. On the 4th of January, 2018, on Sol 4958, Opportunity's front hazard camera took a routine late afternoon image looking downhill, about a third of the way down the valley. The sun was low, which throws long shadows and exaggerates surface texture. The ground was striped, not randomly rough. Striped organized into distinct parallel lines defined by rock fragments aligned with the downhill direction, arranged in ridges less than a meter apart, with coarser grains on the ridges and finer material between them. For a sense of scale, one of the rocks in that frame is about 2 inches across, sitting roughly a meter from the centerline of the rover's front wheels. This was a genuine surprise to the science team, and it looked familiar, which is the dangerous part. Patterns like this exist on Earth. You can find them on Mauna Kea in Hawaii, and there they are formed by cycles of freezing and thawing in ground moistened by melting ice or snow. Fine-grained soil expands as it freezes, and that lifts rock fragments up and out to the sides. Do that enough times, and you get stripes. So the immediate reading was periglacial, shallow subsurface ice. If that were true, it would mean ice had been present in Perseverance Valley, possibly within the last few million years, during a period when the spin axis of Mars was tilted more steeply than it is now, and some of the water ice currently locked at the poles was redistributed toward lower latitudes. The team did not accept the resemblance. They tested it. Mike Mellon, a planetary geologist and geophysicist at the Applied Physics Laboratory at Johns Hopkins University, was brought in to run thermal modeling. At the request of the mission's deputy principal investigator, Ray Arvidsson, there were 2 questions. Is Perseverance Valley a place where ice could be stable? And is there something unique about this valley that would explain why these features are here and almost nowhere else? Squires reported the outcome in 4 words. The answer is no and no. That effectively knocked ice off the list, and the stripes are still there, still unexplained. They do not point directly downhill the way the Earth analogues do. Sullivan has suggested they might be megaripples, a kind of large-scale surface undulation built from material with fine fractures, moved by a bouncing, skipping motion of sand grains called saltation. Something like the frozen wave patterns on a beach or a seabed. Squires' read on it was that they may be looking at something genuinely new. Arvidsson's read was blunter. The stripes cut across the topographic contours. They might be wind ripples, and nobody knows. The other anomalies came faster and smaller. In late April and early May of 2018, the rover investigated 3 pitted rock targets named Tomé, Nazas, and Allende. Their textures and compositions were unlike anything the science team had seen anywhere in the mission, and this was a mission that had been analyzing Martian rocks for 14 years at that point. Then there is the composition problem. Michael Bouchard, a PhD candidate at Washington University in St. Louis, compared the chemistry of rocks in the valley against more than 150 rock targets Opportunity had analyzed elsewhere on the rim. Most of the valley rocks turned out to be members of the crater's impact breccia, the Shoemaker Formation, exactly what you would expect. But 2 cobbles, named Parrel and Masilla, did not match. Parrel was highly similar to a completely different formation, and to a class of rocks that appear blue in false color images and show up scattered along the rim. Bouchard's suggestion is that Parrell and Masilla came from somewhere else, most likely from further up the valley, and were transported downhill by something: gravity, water, or wind. He does not say which. His mixing models suggest that this type of blue cobble makes up something like a quarter of the material filling the valley floor. And there is one more thing, which is really a photograph of a coincidence. Years earlier, on Sol 1784, the rover had taken a navigation camera image showing a fracture in the ground that had reactivated recently enough to offset a large wind ripple. One side of the ripple visibly misaligned with the other, the fracture cutting between them. Fault movement caught in the act on the same timescale as ripples migrating across the surface. Sullivan's conclusion from that image is careful and, I think, quietly remarkable. Displacement fault activation does happen on Mars, very rarely, but it happens, which gives him a mechanism for the valley's uniqueness. An ancient network of fractures and faults, reactivating occasionally across billions of years, with long silences in between, each reactivation lifting one block slightly relative to another, and each new bump immediately going to work being sanded flat again by the wind. He does not claim it is the answer. His final slide at the conference said the opposite: no conclusions yet, multiple working hypotheses, collect more data. He was right to be cautious. He also had less time than he thought. To understand the storm that ended this, you need a baseline. Dust storms on Mars are ordinary. They happen constantly. Most are regional, seasonal, and survivable. They are most likely during southern spring and summer. But roughly once a decade, and for reasons that are still not understood, one of them goes global. It stops being weather and becomes a lid. The entire planet disappears under it. The last one before 2018 was in 2007. That storm cut available sunlight so sharply that both Spirit and Opportunity were put into emergency cutbacks, reducing operations and communications just to stay alive. They survived it. Going into 2018, some atmospheric scientists were already anticipating that Mars was due for another one. The storm arrived in June. It grew until it encircled the planet, and it lasted from June to August. Now, this is where the last images come back into focus, because the rover was not photographing the storm. It was measuring it. There is a number that describes how opaque an atmosphere is. Scientists call it tau. On a normal clear day, sunlight reaches the ground with very little obstruction, and the rover's panoramic camera filters one centered on deep blue light at 440 nanometers. One on red and near-infrared at 750 are built for looking at rocks, not stars. Point them at the sun on a normal day, and you get a white, overexposed nothing. On the 10th of June, 2018, the team pointed both eyes at the sun and got a usable image. That is only possible if the sky is nearly closed. The tau that day was about 10.8. At that value, only a tiny fraction of sunlight was reaching the surface. For a nuclear-powered rover, that is an inconvenience. For a solar-powered one, standing on a slope, in winter, in the southern hemisphere, it is not survivable. The last surface feature Opportunity ever analyzed was a tabular rock outcrop on the 3rd of June, 2018. The team was still wrapping up investigations of those rocks when the storm hit, and there is a final image that almost was. Between the 13th of May and the 10th of June, the rover had been assembling a full 360-degree panorama from its resting place in Perseverance Valley, 354 individual frames taken through near-infrared, green, and violet filters and combined into color. In it, you can see the rim of Endeavour rising in the distance, the rover's own tracks descending from over the horizon and weaving down toward the outcrops the scientists wanted to examine, an outcrop called Isleta del Sur, about 7 meters away. And, at the edges, the floor of the crater, pristine, unexplored, waiting. A few frames at the bottom left are still black and white. Color on that camera requires photographing the same scene 3 separate times through 3 different filters. The rover never got to make the second and third passes on those frames. The mission's project manager, John Callis of JPL, described the panorama as embodying what made Opportunity a remarkable mission of exploration. It was processed and released after the mission had already been declared over. NASA spent 8 months trying to wake it up, sending more than 1,000 commands. On the 13th of February, 2019, the mission was declared complete. Nearly 15 years against a 90-day plan. And now the part that reframes everything. While that storm was quietly killing the rover, 3 other spacecraft were watching the storm itself. And what they saw was not weather, it was a mechanism. Instruments aboard the ExoMars Trace Gas Orbiter had begun science operations in April 2018, before the storm started, and monitored it from onset to decay. They measured a large increase in water vapor high in the atmosphere, between 40 and 100 kilometers up. That should not be possible. Normally, water vapor rising on Mars hits a ceiling. It reaches an altitude where it becomes saturated, condenses onto dust particles, forms ice clouds, and falls back down. That ceiling is called the hygropause, and over low latitudes, it usually sits somewhere between 20 and 50 kilometers. It functions almost exactly like the cold layer at the top of Earth's troposphere, which stops our own water from escaping upward. Global circulation models run for the 2018 storm showed why the ceiling failed. When enough dust is lofted above about 40 kilometers, it absorbs sunlight and heats the atmosphere from the inside. Warmer air holds more vapor. The clouds that would normally form at 40 to 60 kilometers do not form. And with nothing to condense onto and nothing to fall back down as, water simply keeps rising all the way to 70, 80, 100 kilometers. At that altitude, ultraviolet light tears water molecules apart. The models show hydrogen appearing in the upper atmosphere a few days after each surge of water, and hydrogen, once liberated that high, escapes the planet entirely. NASA's MAVEN orbiter measured it directly. Shane Stone, then a graduate student at the University of Arizona, was watching data from an instrument that samples the atmosphere at its lowest orbital pass, about 150 kilometers up. Water abundance up there is normally around 3 parts per million. Over 2 days near the start of the storm, it more than doubled. By the peak of southern summer, it reached 60 parts per million. Stone's reaction to seeing it was that the global dust storm stood out in the data like nothing else. The MAVEN team ran the arithmetic forward. If loss at the observed rate had persisted across Martian history, the planet would have shed a global ocean more than 25 meters deep. Nobody knows whether it has. It might be a recent process. It might be the thing that dried the planet out billions of years ago. Michael Chafin, a planetary scientist at the University of Colorado Boulder, has described what MAVEN may be watching as the tail end of a planetary death spiral, and even he frames it as a possibility, not a finding. But look at what that means for a rover on a crater rim. Opportunity spent its last 2 years inside a valley that looks like it was carved by a river. It tested water, it tested wind, it tested ice, and faults, and avalanches, and a lake that may have spilled over the rim. It found evidence for several of these, and proof of none. Golombek's summary of where the science stood was 3 words long. We don't know. Then he added a 4th. Yet, Arvidsson has a word for the deeper trap here: equifinality, the principle that in an open system, the same end state can be reached by many different paths. A valley that looks like a river does not have to have been a river, which takes you straight back to Chamberlain and to 1890, and to the idea that most geological problems are the product of several processes acting at different times or all at once. So the rover never learned where the water in Perseverance Valley came from, or whether there was ever any water there at all. But on its last morning it raised its camera, filtered out almost everything, and photographed a sky so thick with dust that the sun had been reduced to a smudge. It measured how much light was getting through, sent the number home, started one more frame, and stopped halfway. It did not know what it was looking at. Neither did anyone on Earth. That day, we sent a machine to a dead world to look for the ghost of water, and it spent 15 years finding places where water might have been and never once finding water. And then, in the last minutes it had, with its power draining and its sky closing over, it turned around and photographed the thing that had been carrying Mars's water away the entire time, and the picture came back dark and unfinished, and the sender never knew.